Hey class, I hope that your week is going well, that those of you, if any of you are located along the coast, are coping with the hurricane admirably. Um, I know that we were advised that you may not have all of the facilities that you normally have, such as internet. So, if that affects you, then it will definitely be taken into account. We have a little under a month until our first exam. I don't want you to stress. I am providing notes as we go, and uh, there will be a review which we'll go over either in a bonus video or as part of the lecture the class before. Yeah, we're humming along in this course. It looks like we will follow the pattern that my course last fall went through, where we'll review everything in kind of a high shallow depth once through for the first exam, and then we'll come back and the second time around we'll do it again with a little bit more difficult problems for that second exam. And then for the third exam, again, the third time through the same material. And so really this will give you a chance after each exam to for the first exam, you'll get to deal with a lot of really easy problems, and then for each subsequent exam, as we go through it, you should have an idea of what it is that you're struggling with, or if there are any particular concepts that you really want to focus on, because we're not following the fire and forget model with our course material here. So please do, if you have any questions, feel free to email me or message me, and we can set something up with MS Teams or Zoom, or a phone call if we need to, or if all else fails, then we'll find our way into the campus as well. So we'll see. But yeah, so if it comes to that, then we can. But hopefully, y'all are working your way through. We'll go over homework 1 at the end of class today, but I'd like to review chapter 5, which is an actual chapter that we're going over, and then the notes that I have for chapter 6 regarding counting, and so it's kind of an introduction into probability and some of the tools that we'll use in chapter 7, I believe. So hopefully we can get through both of those today, and it yeah, so we'll go from there. Okay, so let's switch over to the notes, and then after chapters 5 and 6, we'll jump into the homework 1, where as additional incentive, as if you needed any more, I will help you guys get started and on homework 1, and introduce you to LaTeX. Okay, let's jump into it. Okay, so induction, which I really didn't enjoy whenever I was making my way through the undergraduate world, and it wasn't as bad when I revisited it several years later as a graduate student. I don't really know what it is. It just I think for me, when I was learning it, it felt a lot like circular logic. So I have to assume what I'm trying to prove to be true, and then magically it works. Like, well, not exactly, but a little bit, yeah, actually. So there's a prerequisite to assuming that something is true, and so there's basically 2 steps. Right? And so the first step is the basis step, and we have some initial truth that we can establish. And we say, okay, so if I can show that whenever my value k or my value n is 0, whatever variable I'm using, then this statement that I'm trying to prove is at least true once. Okay, and so that's the idea behind the basis step. It establishes some foundation to build upon, and then the inductive step, which I've kind of combined with the inductive hypothesis. So you then assume the inductive hypothesis. You assume the statement that you're trying to prove, where and this applies to like these successive problems like recursion and so forth, right? And so you assume that it's true for k plus 1, right? Where k can really be any number, any positive integer. Then if you can show that when it's true for k, it's true for k plus 1, then you're done. Because you've established some base step. You say, okay, well, if it's true for k equals 0, and I've shown that it's true for k plus 1, then it's true for k equals 1. Right? And if it was true for k equals 1, and it's true for k plus 1, then it's true for 1 plus 1, which is 2. And if it's true for 2, then it's true for 2 plus 1, so it's true for 3, and so forth. Right? And you've really established it just going forward. And so that's the whole principle behind proving something by induction. But it's important to note that, and as you look through these examples, that induction, while a powerful tool and certainly helpful for what it provides, it doesn't provide constructive solutions. So as you look at these problems, you'll notice that we're given some claim, we're given some hypothesis. We say, okay, well, I think this solves your problem, and then you're using induction to verify it. But it doesn't help you find this magical solution, this closed form solution to this problem, or the closed form solution. And so it's not helpful in that regard. It doesn't necessarily solve the problem for you. It just proves something to be true, and it proves it given some initial truth and then a successive truth, so an ongoing truth where you can build on it brick by brick, basically. Okay, so let's take a look at this example. So okay, so this first problem, which we will be revisiting over and over through the semester, is the sum of the first n integers, right? So Sn is the sum, S for sum, right, over n integers, right? The nth term or whatever in this series. And so it's just 1 plus 2 plus 3 plus 4 plus and so on all the way up to n. Right? And so the claim is that for S sub n, for whatever our nth term is, whatever nth sum we're looking at, where we're adding up the numbers 1 through n, that value can be found with a single computation using n squared plus n over 2, or in this form, if you factor out the n times n plus 1 over 2. And so using induction, we're going to try to prove this recursive formula to have this solution, right? And so remember, there's 2 steps, 3 if you count the inductive hypothesis, to proving this truth. Right? So the basis step, whenever n is equal to 1, then we're summing just a single number. We're just summing 1. Okay, so 1 times 1 plus 1 is 1 times 2, divided by 2 is 1. And so the sum, the number 1, right, the sum in this form, in the original form, the recursive form, is equal to the closed form solution. So it looks like this closed form solution holds for that trivial value whenever we're just testing the first number. And so this is where we make our leap forward, right? Our leap of faith, basically. So we say, okay, well, if I have that it holds true for the first k numbers, where k is possibly just this very first number, then I believe that it will hold. So the inductive hypothesis is it will either degenerate and fall flat on its face if I give it one more number, or it will hold true for that very next number. Right? And so in order to stitch these two together, our assumed truth with our function definition, our recursive function definition, we need the inductive hypothesis, right? And so you'll see that we bring them together. We bring the recursive formula together with this formula by using our assumed truth. Okay, and the basis step, and you will get some problems where the basis step is false, the basis step fails, in which case the closed form solution is not a solution. So when you get that on the test, don't be surprised, right? Okay, so coming back to the problem, then we have the inductive step. So we have assumed that this formula holds true for the kth number, that our closed form solution takes this form, and that it's true. And we're going to show that either it will be reduced to the absurd, or it will hold true for k plus 1. Right? So now this is where we stitch it together. So we have s sub k plus 1, right? So we're summing over k plus 1 numbers ranging from 1 to k plus 1, and this is just our little counter here. And because this is summation, it's 1 plus 2 plus 3 plus yada 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 up to plus k, and we stop after we've included this last number up here, so plus k plus 1. So k plus 1 is a number, it's 1 larger than k, right? So it's addition, so we can just pull that out, and now we've reduced this to one number plus some other sum. Well, we've already assumed through the inductive hypothesis that this formula will hold true for our first k terms. So we can make a substitution here. We can replace this sum. We're saying that these two are equal, right? These two are equal. This is Sn, this is Sn. So we can replace this with this. And so that's exactly what we do here in this step. So we've simplified it so that we have some new value and some previous value. And then we make a substitution, and I include this step so that you can see that s sub k is equal, by definition, to this, and by assumption to this. Okay, and so that's what's going on here. That's where that substitution is coming in. And so now we have just k's going on, and we just want to combine them. So we get a common denominator here, right? So multiply by 2 over 2 over here, right? And then with the common denominator, we can just add them together. Right? So 2k plus 1 times k squared plus k is equal to k squared plus 3k plus 2. Okay, and then that factors into k plus 1 times k plus 2 over 2. Okay, well, if we substitute k here with k plus 1, then this becomes k plus 1, and this becomes k plus 2. And so s sub k plus 1 is equal to k plus 1 times k plus 2. Well, that's exactly what we have here. So again, the inductive step is it's essentially challenging the assumption that we made in the inductive hypothesis. So yes, we're assuming our closed form solution to in fact be a solution, but we're challenging it to either prove itself or fall flat on its face. and if it's true, if it holds true, then whenever we make our substitution for some previously established value, what we assumed to be true, and we challenge it to solve the very next number in the sequence, in the counting sequence, it holds form. It comes back and it finds its way to that closed form representation. And so when it does that, and this is important, and we have established a basic truth, some base step, then the ability to start somewhere, the base step, and to always go one step further means that it holds true, for any value, any integer larger than that base step. Right? So that's the spirit of induction there. Okay. Okay. So strong induction is essentially the same thing as induction, but with induction we're either starting with 0 or 1 as our base step, and strong induction essentially jumps ahead and it says, okay, well, I can give you that it's true for k values. Can you show that it's true for k plus 1? Well, yeah, that's basically induction, right? Like there's not a whole lot of really additional interesting things happening there, but I do want to take a moment to talk about something else real quick. Okay, so this is a Rubik's Cube, or a friendly alternative to the Rubik's Cube, which is exactly similar in principle, right? And so the principle of strong induction, as applied to the Rubik's Cube, is that if you have, let's say you've turned it, just a single rotation on a face, then the cube is no longer what we would consider in solved form, but we've only taken one step. Okay, and so we know that if I just turn it back, if I turn it back the other way, that I can get it back to a solved form. Additionally, if I turn it that one face and then I turn it again another face, right, then it's even more broken or less solved than it was before, but it's still just one additional rotation from something that we knew to previously be solved, right? So we know that we can always get back, right? And so it was true for one step, and it was true for two steps. So if we do it a third time, okay, it's again even further from our initial, our base step, our base solution. But just as before, because it's an invertible operation in this case, right? Like it's not always what we're talking about with induction, but in this case, in the Rubik's Cube, then we know that we can get back to a solved state, right? And so whenever this was the Rubik's Cube became really popular in the 80s, there was this craze, and it was such a frustrating puzzle that people wondered whether or not it was even possible to solve these states or whatever. And so because of that, right, because of strong induction and the idea that each rotation is only one step further removed from some previously solved state, then that it is always solvable. And so the only exception is if perhaps you take off the stickers and you rearrange them in some fashion where it's not actually solvable anymore. Right? So like if you, so white and yellow are on opposite edges. So the solved state is going to have yellow entirely opposite, right? So if you replaced this blue one with one of the yellows, then you would have white and yellow next to each other, and that would never be solved, right? So it's possible by removing the stickers, to get to something that's truly broken. But through rotations and the principle of strong induction, the idea that if it was true for k plus 1 rotations, right, for some state where all you did was kind of mangle it through rotations, then regardless of what action you take, you can still get back to a solved state. And so the interesting thing, so the existence, right? That's existence and versus uniqueness. The existence of a solution is easily proved using induction or strong induction in this case. But the fact that the solution isn't necessarily unique, that you don't have to rotate back the way you came, right? So we made one rotation. We say if you go back the way you came, that you can get to a solved state. But that same one rotation is also solved through 3 additional rotations in that same direction. And so those solutions, like there is one solved state, right? Obviously, it's whenever the all of the faces have the same color. Then but arriving at that solution can happen through more than one path, and so I think that was the really interesting thing about the Rubik's Cube. Okay, so jumping back to the notes. Okay, so just going through the sections, I also try to highlight the definitions as well as the examples that I think are interesting. And so the well-ordering property, it's something that we intuitively understand, but as we build our math vocabulary, I think it's interesting or important to take note of these terms. And so some of these concepts that we know and but we can't quite explain why it's true or whatever. It's very helpful, I believe, to learn these definitions of these really simple and intuitive concepts, just so that we can explain ourselves better, and it kind of cleans up our thoughts as we try and go through and prove some of these things. So the well-ordering property, again, is something that you're all very familiar with. So if you have a set of numbers, right? If you imagine just writing a bunch of numbers on a paper and then cutting it up and so that there's a number on each square, you cut the sheet into like 100 pieces or whatever, and you toss them in a sack, or you do it with just one or more pieces, right? So some non-empty set, so you at least have one number, right? And you haven't done it infinitely many times. That's the other key. So you did it more than 0, and you did it less than infinity. Then it's going to have some largest number. It's going to have a maximal element. And so this is the concept of well ordering. And so on the one hand, yeah, it is extremely intuitive. It's something that we all kind of understand with numbers. And so you think, okay, well, wouldn't that always be the case? And so not exactly. So there are, I'd mentioned in a previous lecture that there's the concept of posets, partially ordered sets, where you can have like a lattice structure or something like that. And so you can establish that certain child elements are less than some parent element, but you don't necessarily have that siblings or cousins or whatever in this structure relate in any way to one another, and so you don't have that well ordering property. In particular, the relationship operator, the less than operator, doesn't necessarily assign a value of either true or false to every pair of possible inputs. And so it's a little bit of a foreign idea, and I'll mention it again whenever we come across an example of this. So in my mind, I'm thinking of a group lattice, but we don't have the background established necessarily to discuss that, and I'm trying to think of another example that perhaps you might be familiar with. Okay, yeah. So here's an example. So as students at a university, then there is this, I suppose, implied sense that, our hope, that the individuals teaching you will have some more established level of knowledge in a particular field. Hopefully, the class that they're teaching you in, they'll know at least something that they can teach you that you didn't already know, right? And so, in a very humble way, we can make the claim that these instructors would each know more than the student who is attending the class in whatever given subject, and presumably having all received a bachelor's degree ourselves, then we would have taken each of the classes and have, assuming we didn't undergo some dramatic synaptic pruning along the way, we would have at least a better understanding, perhaps in each of the areas of study for a freshman or a sophomore. And so the relationship between student and instructor would hopefully imply that the instructor knows a little bit more in the given subject field, right? Though perhaps not necessarily in life in general, right? But if we restrict it to just the curriculum of the undergrad. But there is no relationship necessarily between the instructors themselves, right? So we have this partial ordering where the pupil knows less than the master, but there is no comparison amongst the masters themselves, the instructors, right? And so that structure would lack well ordering. We can't just sort and say, these individuals know more than other people, right? And we also see that, with parents and children as well. And so you would assume that parents would know more than children, but you wouldn't necessarily be able to compare the parents among each other because everyone kind of has their own level of expertise. And so, like, even the greatest scientists, you can stick them in front of a guitar or a piano or whatever and ask them to sing something, right? And suddenly, this very accomplished individual can quickly be humbled by something that other people can do way better, right? So that's an example of a partial ordering where it's just not really well defined, necessarily between certain members of the set, but you can make certain comparisons, for in these examples where younger individuals would presumably know less than the older individuals, or vice versa. The older individuals would presumably know a little bit more than the younger ones. But beyond a certain point, you just can't make a comparison. But numbers don't have that problem, right? The integers don't have that problem. You can compare any two integers, and you would get some less than. But complex numbers would lack that, right? So the real numbers are a subset of the complex numbers, but if you get off of the real line, then you can't necessarily compare any two complex numbers as less than or greater than. There are certain things, like if you just take the modulus or the absolute value of it, which would again get you back to the real numbers, then you could do that, but in general you can't, right? So that's the well ordering property, which basically says if I stick a bunch of numbers, a set of numbers in a stack, then one of those numbers is guaranteed to be the maximal of the set, and vice versa, or conversely, one of the numbers would also be a minimum. Neither one necessarily unique. It's possible we wrote the same number more than once, but there would be a minimal and maximal value in that, and that's well ordered. And then the other cases would be not well ordered, right? All of those other scenarios we discussed. Okay. So recursive, instructional induction, yada yada yada. Okay, so we'll start talking about a tree. We've kind of already introduced the concept, and a rooted tree. You can think of like a family tree, I guess. So it's if you come from a conventional family, then you would have one set of grandparents, and you just looked at one side of your family, right? Then you'd have a set of grandparents, and they would have had their children, and they would have had the parents, and the aunts and uncles would have had the grandchildren, and so forth. And so that would be an example of a rooted tree. If you stopped it at the grandparents, I suppose you could do the same thing with great grandparents, or continue to go up. And so the example breaks down in that we can continue on past the root in these examples, but anyway, the structure is something familiar, right? The family tree is a familiar object. Okay, and so the points, in this case, the aunts and uncles, would represent the nodes, or the vertices, the vertex set, and the edges, the ones that show the relationship between parent and child. Those lines would be the edges, and so a tree consists of, or a rooted tree. Consists of a root node, and then which is part of the set of vertices, and then the edges, and that's it. So it's the set of vertices and the set of edges. Okay, and so this example with a recursive definition, it basically says that if you start with a single node, so a loving couple, in the grandparents example, right? Then you could extend the tree by adding any node to any level, basically, and connecting it to some parent node, and so. As long as you only connect the new vertex to one node, then you will always have a tree. And so this is something that can be proved through, as we call it, structural induction, right? And so the structure of the tree is maintained by ensuring that we're not connecting we're not creating chimeral species, right? And going in the lab and splicing DNA and selecting chromosomes from multiple sets of parents, right? Like we're knocking out the mad scientist aspect of this, and maintaining the structural integrity of this object, or this entity. And so basically you through this method you will always get a tree if you're only ever connecting the new nodes to an existing node. And then what this is saying is basically that more than that, if you took the root from some other tree and then you connected it to some other node, then you would again have a tree. And so extending the family tree example basically says, okay, so if we went back and we found the great grandparents of whatever example this is, then they would be a rooted tree. And then down the line, someone that builds family trees or whatever, right? Some Ancestry.com or whatever, right? So they've established all of these independent family trees, and then they realize that several of these people are siblings, and then they connect them to some other tree, right? So what was previously a root in a tree now becomes some child, because they found your great-great-grandfather and grandmother, and now you can make that connection. So you just connect it to an existing node in some larger tree, and what was previously an independent tree is now just a branch on some larger tree, right? And so that's what this is talking about in very formal language. Okay. And so here's an example of binary search. Binary search. Okay. Okay, so let's discuss this just a little bit before we dig into the code. And so we have well, let's jump into the code, I guess. So we have our set of integers, and you'll notice that they are sorted, right? It's right there in the name. and you can verify 10, 34, 56, 75, 100, 2005, and 2019. Right? And so we have this sorted set, and we can tell through size of, or in Java or C# or JavaScript or Python or basically any other language, we can use a length property to get that value. But in C, we can use size of divided by the size of the items being stored in the array, right? Which is why we're dividing by 4 here, because integers are 4 bytes. To get the number of elements in the array, and then the max index is going to be 1 less than that, because we index beginning with the number 0 in arrays in programming, as opposed to math where we index with 1, right? But so the minimum index is 0, and the maximum index is 1 less than the size of the array. So instead of counting from 1 to n, we count from 0 to n minus 1. Right? And so binary search basically just recursively splits the difference here. Right? And so if we're looking for, let's say, 150, and we know that we have a sorted set, right? A sorted collection of integers, and this is key. You cannot, this algorithm does nothing if the list is not sorted first. So let's say we're looking for the number 150. Then what binary search does for us is we start in the middle, right? We have our min and we have our max, and we take the average of the two, right? And we say, is our number bigger than whatever number? Well, first, is it equal to the number that I found at that location? So sorted items, the midpoint index, and 150 is not. And so then the next thing we ask is, okay, well, is it to the left or right of that number, right? So is it less than what I found? And if we're looking for the number 150, then it is not. We say, okay, is it greater than? So it is in that case. And so then we say, okay, well, if it's greater than, then we need to establish a new minimum index, right? And then we'll call that same function again, but we'll pass in the new min index. So our maximum index, length minus 1, is unchanged, but our min index was moved forward by half the size of the array. So if we were looking at these one by one, then we wouldn't have reached this result until after 4 tests. But because we're using binary search, we were able to eliminate half of the list after just a single test. Okay, so that's pretty good. And so we take the average again, and because whenever we cast it to int, we get the floor. The next index is right here, and so we again ask, is our number bigger or less than what we found? It is bigger than 100, so we again increase the floor, and now our average between here and here, average index, not average value, right? So our average index will put us here, and so we ask, okay, well, is our number bigger or less than that? And it's less than, so we know it's to the left. So now we have this and this, and we see that so whenever we take our average, right, and we truncate the value, we'll see that our midpoint, our min and max are the same number, and it is not equal, so we'll return -1 to indicate that our value could not be found, right? Couldn't find that value in the collection. Okay, but if we were looking for the number 56, then this recursive search would have it started in the middle again, right? So we take our two items, our two indices, right? This 0th one and this n-1. And then we jump to the middle and we see, is it left or right? And it's less than, so we go left. And then it taking the floor of that gets us to this index. We say, okay, well, is 56 less than or greater than that? It's greater than, so it moves to the right. And then on the third test, we find that 56 is this value, and that gets returned. So this algorithm, this recursive algorithm, and it's recursive because we're calling the same function over and over again, just like we were with Fibonacci, but in this case it's a more productive function. And so our recursive algorithm will complete in log of n steps, where n is the size of the array, and that's log base 2. Because we keep cutting it in half. And so for a small array, I mean, you can look at it and say, okay, well, 56, it took 3 steps to find 56. Had I just started at this 0th element and gone forward, then I would have found it on my third test. It's not really any better. But if you consider, an array the size of a million or a billion, and you're able to find any item in the case of a million, it would be 20 steps basically, as opposed to potentially a million steps, or in the case of a billion, you would find it in about 30 steps, or less than 30 or fewer steps, as opposed to a billion tests. Then this algorithm starts to be really, really, really wonderful. So it's really great. And so this is one of the reasons that as you're dealing with data, that it's really nice to have something that is always kept in sorted order, right? And so whenever we discuss databases and database keys, you'll understand why we keep it sorted, and it's because if we want to look for it, we want to be able to find it really quickly, and so by having something that's sorted, we're allowed to use something like binary search, and again, kind of the spirit of this class is finding ways to deal with these problems as they get really large. If it's just a single user, then you can be as terrible as possible, and it's still pretty good because the computer's really fast. But if you're dealing with thousands or millions of users, then you need to be scraping the theoretical limits of what's possible in order to perform well. And so for that reason, it's nice to use structures and solutions that keep things in some sense of order. And so that's the concept behind indices in databases and clustered indices, which basically means that you have some serial number that gets stamped on each record, right? And it's sequential, right? So you can start with 1, or you can start with any arbitrary number. Some people start with 1,000, some people start with 100,000, some people start with 1,000,000 or whatever. And then the next record is 1 greater than that, and so forth. But it's always kept in order, and the data, as it's stored in the file, it accumulates, but it's kept in order. And so whenever you go looking for it, it's pretty easy to find it. You start with some value and then you jump to the offsets, or if you're looking up at the index, then then you search the index using something like binary search to find what data page that the value is actually on, and then you jump to that, and then you find your way from there. And so these optimizations are built into databases, but we have to understand the principle of what it is that's there to be taken advantage of as computer scientists. And so that's one of the reasons that sorting, either taking something that's unordered and putting it in sorted order, or as we go along to maintain some some order, some sorting order. That's why it's so important. Okay. And so this is that same binary search, but in Java. So if you're more familiar with Java, then that's fine. And yeah. Yeah. We could implement it in JavaScript. If you're, enterprising and you want to give it a shot, try to implement these in JavaScript. So it shouldn't. I imagine it would be closer to C. You wouldn't have any imports. You would define the function. Here, let me. Yeah, okay. We can just do this. So almost everything would look the same, right? So you define some function. So we'll just say function. Right. Binary search. It takes in sorted items. So if we're using TypeScript, then we'll define some typing. But raw JavaScript does not. Here, let's define this as a variable. So JavaScript will let you play with how it is that you declare your functions, because they treat them like a special type of object, but they're still a first-class data type in JavaScript. Left, right, search file. And I'm hitting Shift Enter whenever I want a new line, because I don't want it to actually execute the code just yet. So if you're having trouble repeating my results, that's the key, is to hit Shift and then Enter at the same time. Okay, so then we declare our midpoint variable, midpoint index. And we want the floor action here. Also, I should note that JavaScript only has a number data type. It doesn't have a int or double or long. It just has the 64-bit number, which is essentially a double. So everything is a double in JavaScript. Parse int returns an int, I guess, internally. But as soon as it can, it gets converted to a double. Okay, so we're taking an average, right? So we have left plus right divided by 2. Okay, and then we do our series of if statements. So if the value that we're searching for is equal, and you'll notice that in JavaScript I use triple equal to. So we'll go over this later. It's essentially, it's what you would expect from the equals in every other language. But JavaScript was written for people that, this might be a little harsh, but that don't have a terrible amount of programming experience, and so it tries to help you out. And so if you use double equal to, then it will do its best to make those values equal. So basically, if you have the word, which the string of the number 7, and you compare it to the actual number 7, as opposed to this, right? Yeah, let me show you. Alright, so in JavaScript, this is equal, right? But this, the triple equal to, that's not true. And so, yeah, I am opposed to that version of equality, so I always use the triple equal to whenever I do my comparisons in JavaScript, so feel welcome to take that advice. Okay, so then we have our sorted items, and we search for our midpoint index. And if it's true, if we found the number that we're looking for, then we return the index of what it was that we were looking for. Right? Else, then we check to see if it's left. Right? So search val is less than sorted items midpoint. And that left is less than our midpoint. Basically, we have this in here, right? Because we don't want a Stack Overflow exception. If we don't have that value and we reach a point where midpoint is equal to left and midpoint is equal to right, so basically where our two endpoints, our bookends on the array, have converged and we didn't find the number, then we'll essentially recursively call this function forever if we don't have this additional condition in here. And so, yeah, we don't want to do that. This one should have a new line. So we're making another call to that same function. All right, so this is the recursive element of this implementation. So we pass it those same values, except that because, so our left bookend stays the same, but because it was less than the midpoint, we can move our right bookend to what was the midpoint on this test. And in fact, we can do one better. We can move it even further to the left, and that's why we have our strict equal to here. Else, otherwise, we check to see if it's to the right. But this time, our right bookend stays the same, and our left moves one closer to the middle. And if neither of those, or if none of those three held true, then we return -1 to indicate that it wasn't in our array. Yeah, I intended to do this as an arrow function. As a beginner, you probably want to just declare this as a function. Okay, so now we can call that. And main, well, we're using an interpreter, so we don't really need that. We can just start putting our stuff in. So sorted items we'll declare as an array. And we'll do 2020 this time. Min index is 0. Max index. Yeah, this is terrible. let me fix this. Right. So I've declared this on the global object, which is terrible practice. I mean, maybe the website that I'm using actually needed those variables and I've overwritten something. And so it's always important to declare some form of scope on your variables in JavaScript. So we're using an interpreter and we have access to basically everything, but we don't want to declare our objects on the global scope. We want it to be limited to this, basically. Right? So we'll use let or var or const if we never intend to change it, but for the most part, you probably want let or var whenever you're declaring your stuff. Okay, so we're just redoing that. I mean, it's kind of nitpicky, but I should know better, and so I should be teaching y'all better. Okay, so we're looking for 56, but we can change this value later if we want. Okay, so then we'll get our match index by calling our function, and it'll call itself recursively. So we pass it our list of items, our left index, which our left bookend, which we start at the very 0th item, and we end our right bookend at the n-1th item. Sorry, I don't know where my head is at. Max index is not 0. It's the length minus 1, right? I mentioned that before. Okay, so left, right, and then search val. And so these variable names match up really nicely. Right? Okay. Oh, just as I was complimenting myself. Okay, so our left bookend is our min index, and our right bookend is our max index. And so it says it's at 2, right? So let's test that. Sorted items, match index, and the value is equal to our search value, right? We're looking for 56. We found 56. Okay, so what would happen if instead of looking for something in the array, we look for something that was out of it, like 1,000,000? Then we would get -1 to indicate that it wasn't in the array. Okay, so my mistakes aside, which hopefully showed you that even with years of experience, the mistakes are unavoidable, but you do try to pick yourself up quickly from them. So those mistakes aside, that's an example of how you can translate from one programming language into another. So you end up doing it line by line, but the logic is extremely similar between these languages, and hopefully the example in C and the example in Java will show you that. Okay, so iteration. Okay. So earlier I'd mentioned that these recursive functions, it's possible to replace them with loops instead of the recursive function, because even with a properly defined function, it's still possible to get a stack overflow, and Fibonacci is a perfect example of that. Just if your input value is large enough, then you can overflow the stack in a reasonable amount of time. And so it's preferable from a memory footprint standpoint to use a loop instead. And so here's an example of how we would use an iterative version of Fibonacci. And I would encourage y'all to try writing it in JavaScript. Just translate it from what you have over here. Remember, just inspect and then go to console, and you'll have the interpreter. And so give it a shot, see if you can implement this and test various inputs. But basically, instead of calling Fibonacci over and over again, we maintain the variables as local variables, function variables, and then we iterate over those. Right? So if n is less than or equal to 0, then it's not a part of the sequence, because our sequence, as defined, starts with 1, and both 1 and 2 are given to us as our base conditions. The value is 1, and so really we don't really need to start our loop until we get to something larger than that. Yeah, I'm not convinced that this isn't buggy, right? So before I'd corrected it so that F0 and F1 were both 1, and I think that should really be the case here. So as you're implementing it, and you're wondering why it is that the sequence is messed up, this should be if n is less than 0, right? And so if it is 0, or if it's 1, then it's the value that you return is 1, and the next value in the sequence is 2, right? But we would begin our value I, which is part of our loop, at 2, as here. So this should be 0, this should be 1, this should be n strictly less than 0, as opposed to less than or equal. And then the rest of this should add up properly. And then, right, and so this, so we do our sum, right, which uses the previous values, and then we reassign our previous values. So as we count from, so on the first pass, this would be F0, this would be F1, and then this would be F2, right? So whenever we look to compute F3, then the inputs that we need would be F1 and F2 added together to make F3. So F1, which was previously this value, gets copied on to this one, right, the n minus 2 condition. F2 gets copied on to the n minus 1 variable, right? And then with F1 and F2, we can compute F3 on the next iteration of the loop. But when the loop breaks, then whatever that last value is, that's actually stored in Y, right? And this is inaccessible because it's declared inside the loop, right? Which is why we're returning Y here. So give it a shot. Let me know if you run into any issues. But you should be able to compute the sequence with that, right? And so use this as an example. Okay, and so for those of you that are more familiar with Java than C, then you kind of have your same thing going on here. Merge sort. I don't want to shortchange merge sort, but I do. I guess we'll get to counting next time. Yeah, we'll come back and we'll start with merge sort next time. It's not overly complicated, but I don't want to do it an hour into the lecture, whenever maybe your mind is a little bit tired, even with the chance to rewatch these videos. I still feel like we should start off there. So we'll take a look at merge sort, the recursive merge sort, and the in-place merge sort, which is just a variant of it, at the beginning of the next one, and then we'll run through chapter 6 and do whatever else we can. But now let's jump into the homework. I will spot you all one problem, so you can get familiar with LaTeX. You can see what it's like to kind of operate in it, and hopefully that will be sufficient incentive to kind of push you all in the direction of using LaTeX as opposed to writing down your answers and taking a picture. You can do it, right? I'm not going to stop you. No other course section is actually making anyone use LaTeX, but I think it's always important to present yourself in as impressive a manner as possible once you get out in the corporate world or whatever. And so this is just another opportunity to kind of distinguish yourselves from any other individuals that might be competing for the same work. And so, strictly speaking, it may not come up, but it never hurts to have an additional feather in your cap as well, right? So plus 50-point bonus, come on. I will spot you the first problem on this. All you have to do is copy it into your own editor and type it out yourself, and hopefully get a feel for it, and getting the chance to watch someone work through it. Hopefully it'll take away some of the intimidation behind it. So let's do that. Okay, so the first thing I want to note is that anything that begins with a percent sign, is completely deletable. I downloaded this as a template. It's part of here in the comments. You can delete it and it'll still recompile just as well, in theory, and in practice. Excellent. This is all header information. So whenever you're in C or C# or Java or whatever, you're importing packages or you're declaring using statements or includes in C or whatever. And so that's all that's going on here, is we're declaring all of these other packages that have various other formats and symbol packages and stuff like that. And so we're using LaTeX for math as opposed to typing out a newspaper or something, right? So we're importing these. And then there just happens to be a bunch of other packages that whoever created this template thought would be important. They declared this number formatting for the sections, so to make sure that you start with 1 as opposed to 0 and so forth. But you can skip right past that. So to be completely honest, I'm surprised that this has never really caused issues. Right? So let's try this suggestion and see what happens. Yeah, it seems to have worked. Right? And so A4 paper size is this absolutely enormous paper size. I think they probably use it for like architecture diagrams or something like that. I have never printed anything on A4. So I'm a little surprised that never came up. It's part of this geometry declaration. But yeah, I don't understand why that has never caused a problem. But it always seems to have created the documents in letter. But yeah, why not have it be correct? So okay, so it seems to be working. I didn't break anything. But you don't have to do that. You're submitting it electronically, so it's not going to try and print A4 regardless of what you do. So you scroll down a little further into the title section. We have this header stuff. We have the homework number. You have your instructor name, and then you put your name, right? So Johnny Doe is going to create this homework. And so this first one is just an example, right? And so I included it so that you could use it as a guide, kind of like what I'm doing for you now. But I included it so that you could see how to create bold-faced text BF, and then what you put between the curly braces is going to show up as your text. And so the text itself, usually whenever I'm working, I wrap it inside paragraph declarations, and so that kind of manages the spacing for me and indentation and so forth. But I didn't do it for this one for whatever reason. And so this is an example problem, both to introduce you to induction as well as to introduce you to LaTeX. And so I go through and with the intent that you could essentially copy this and paste it below, and then make the changes to the math to get it to show up appropriately, right? But we won't do that. We'll type it out ourselves. So these two will be on your own, but I will do this one for you. And it will be a graded problem. So as long as you watch this video to the end and you are willing to type it out on your own, then you've got I don't know, I'd say you have at least a 93 or an 83 at this point, right? So okay, so let's do this problem. All right. I like to usually have 3 lines of white space between. Right? Okay, so declare that we want boldface text, right? So we get the answer to show up. Right? Control S compiles, perfect. Looks all official and everything. Okay, so then we define our sequence, just good habit. Okay, so to get the sub indices, right, then you need to do an underscore, and you notice that this one doesn't have it, but this one does, right? So let me show you. Okay, so that's fine, but if you try and do it like that, where everything is just kind of in this one word or whatever, LaTeX will assume that basically it limits you to just a single character. And so even if it's a command, right, even if this is like /gamma or whatever, it's not going to compile. If you want more than one letter, right, then you don't get to use the shorthand. You have to explicitly do the underscore and then the curly braces. And then it'll stick whatever you put in there, and however long right? So you get it all as this subscript, right? And so that's just the convention that's used. It hopefully shouldn't be too foreign to you already, having had some introduction to programming. Right? Okay, so completing our declaration of the recursive function. Okay, so we've defined our recursive function, and the next thing that we want to do is show what it is that we're trying to prove as a solution, prove or disprove. So we want to show and again, this backslash square bracket backslash square bracket enters into math mode, and so it centers the text. It gives that nice little italics font to it or whatever. But it breaks if you have nothing in there. At least I remember it breaking. Well, it's tolerant now, but I remember it breaking. So as a habit, it's always nice to at least include some text in between those whenever you declare it, but whatever. It seems like Overleaf is tolerant of that. Okay, so then and this works fine for just a single line, the square brackets that is, but I'll show you how to handle multiple lines here in a minute. And so this is superscript notation, which you would use for exponents and stuff like that. Okay, everything came out just fine. Okay, so I use these square brackets whenever I wanted it on a new line and centered. I use the dollar signs whenever I want it to appear inline. Right? That's inline math mode. And whenever you use $1 I think if you do that, yeah, it automatically adds the second. And that's just good practice, because anytime you open it, you need to close it. Otherwise, you're going to run into issues. Okay, so now if we want multiple lines, then we need to align our text. And so A, B, C. Okay, so it centers it, and then if we want to align it, we used an ampersand on the line, and we see that these ampersands, wherever it is, that gets lined up vertically in the display, right? So even though it's not lined up together over here, it is whenever you actually compile it. And so I always tab over an extra space whenever I do that. And so the other thing is, well, why do I include that asterisk? And it's because it numbers it if you don't, right? So if you want the numbers to appear over here, like in math books or whatever, you see the equation number, yada, yada, yada. Well, if you don't include the asterisk, then it'll number it for you and stick it over here. But I typically don't use those, so I omit them. Okay, so finishing off the problem. Okay, so we have our formula, and we want to establish that it's true for some basic values, right? So A0, we plug into our formula, the closed form solution, because we're already given these values for the recursive one. Like, that is how it's defined. Right? So that's 5. Okay, so plugging in, right? So the in on the left side is the subscript, and on the right side it's the exponent, right? So making those substitutions, and just doing the arithmetic, we get that A0 is 5 and A1 is minus 5, and okay, well, that just establishes a base value for us in the closed form. Okay, so then we have our base case. Oh, okay. So we have these initial values, and we establish using those initial values that we computed, right, to show that it could be a solution. So we computed the initial values in this case using the closed form. And so our base case is given by our first usage of the recursive formula. So 15 plus 20 is 35. Okay, so this is our base case, part of it, right? So this is essentially our initial condition, and so we need to verify that whenever we plug in it into the closed form solution, that it agrees, right? So we weren't given any initial conditions, so we used the closed form to compute them for those first two values. And that gave us the ability to compute at least a basic value, because we now had two initial terms, a first value of the recursive formula. And then we need to establish that it's true for the closed form. So that so 2 times 16 plus 3 is 35. So the recursive agrees with closed form. So we've established that for at least a basic case, right, or base case. So now, using the inductive hypothesis, we assume that a sub k is equal to 2 times minus 4 to the k plus 3 so basically we're assuming that the closed form holds for other values. And now we put it to the test. We say, okay, so put up or shut up formula. If you're true for k, which we're assuming, then you have to be true for k plus 1. And so this is where we're going to make our stitching together of the recursive formula and the closed form solution. And it'll either break down, or we'll see that we recover the closed form version of k plus 1. So we're expecting something that looks like that, right? And so this is essentially what you do every time you do an inductive proof, or a proof by induction, is that you're assuming that it's true for k, and then you'll use the recursive formula and show that if you go one further, that it doesn't matter whether you compute it by recursive formula or by closed form, you end up with something where if you just substitute k with k plus 1 in the closed form, where that's true. And if you can't get it back to that, then the formula broke down, it just wasn't true. And then remember, you're always also testing that base case as well, because if it wasn't true at the base case, then you didn't need to go through with the rest of the junk, the rest of the important operations. Okay. So to compute a sub k, right, we need a k minus 1 and a k minus 2. And so we use the closed form to get those values. Because we're assuming that it held true up to the value k. And so we're assuming that they were interchangeable up to the kth term in the sequence. And then we'll use that assumption combined with the base step to prove the rest of the way. Fix this. We actually want that. So we've assumed that is true up to k. And then we're trying to solve for k plus 1. And so this left-right stuff, I just want the parentheses, but I'm doing left and right to show that if I end up with a fraction or superscripts or whatever, I want the parentheses to be at least as tall, or at least as high and low on the text so as to appear pretty, basically, whenever it prints out. So the minus 3 is here, and now I'm substituting a sub k with what I had up here. You can copy paste for the substitution, and the parentheses are just to show that we're copying and pasting. And so now I'm making this substitution, so 4 times a k minus 1. And so simplifying, right, you just multiply this here, and this times this, and this. Right. You get the minus 6, minus 4, k, minus 9. Right. Again, it's minus 3 times positive 3 is minus 9. Let's make sure that everything is going to display correctly, that we haven't broken everything. I should really be doing that line by line, but I'm familiar enough that I'm proceeding with the idea that I can fix it if it breaks. And so I'll just copy the previous line and make my simplifications. Right? So here, now what I want to do is I have these, which is fine, but I want to combine the numbers that aren't attached to anything. So 12 minus 9 is 3. So that's an operation. And then again, just copying the previous line and making my simplifications. I have so now what I want is to pull out a minus 4 here, right? So I have this k times, I have negative 4 multiplied by itself k times, which is also equal to negative 4 times negative 4 to the k minus 1, right? Like that's still, if you combine these, it's still negative 4 multiplied by itself k times. I've just pulled one out. But now I have these exponents that are in common, right? And so that is a nice thing to have. So this simplifies to 24, right? And then I have just pulling this out, right? A little centered dot to show that there's multiplication happening, right? C dot. And so now I've factored out this negative 4 to the k minus 1. It just comes right out over here. And then this is simple addition. So that's 32. Okay, but I'd predicted that it would look like that, right? So where is that? We have k minus 1, but we wanted k plus 1. Okay, well, so we'll do a couple more steps here, right? So this is equal to 2, right? Okay, and that is equal to negative 4 squared, right? And that is equal to this plus 2. And you don't have to take as many steps. You can simplify along the way if you want. But I want to be very clear as to how we got this magical result. Yeah. Okay, and then we'll just put this little marker to indicate we've reached the end. Okay, so yeah, it's not terrible, I hope. So I hope you understand both the inductive work that went into it, as well as the, so you can see how we're combining these concepts of the recursive formula and then making the substitutions to get something that relates back to the closed form solution and show that they are very much the same as you iterate forward, and then to give some credence to the closed form solution. So do something similar for these last two problems, and hopefully it shouldn't be too difficult from here to get something very near 100 on this first homework and using LaTeX. Okay, well, have a great weekend. Good luck with the rest of the homework, and I will talk to you all on Tuesday.